Welcome students. Now in this video we are going to see the kinematics and dynamics of this electrochemical machining. Let us we are having this is the tool and this is the work. In between we are having electrolyte flow velocity as V and this distance between two surfaces as Y. Okay, so see here, as shown in the diagram, we are having the set of the electrodes which are plane and with the parallel surfaces, and this work is moving with the constant feed velocity in the negative y direction, okay, normal to the surface of these electrodes. Let us say here the plane and parallel surface set of electrodes. Of course, the upper electrode, that is the work, is moving with constant, say, feed velocity, say F, in negative y direction, that is normal to the surfaces, electrode surfaces. Okay, and if we assume that the problem is of one dimensional and the instantaneous distance between the distance from the work surface to the tool surface is the y, and instantaneous distance from the work surface to the tool surface as y. Okay, and of course the work is made up of pure metal, no alloying is there, and we know that for pure metal how this Q, material removal rate, is given as, that is AI divided by rho FZ centimeter cube per second, isn't it? And here if we are having the over voltage across these two electrodes, that is delta V, and applied voltage is V, then the density of flowing current, simply I can say current. How to get this density? That is J is equal to K into bracket V minus delta V over what? Y. Where K is what? We know that where K is conductivity of electrolyte. And Y is the distance between these two electrodes, we can simply say. Isn't it? So we know this much things. Now see here. Now here, when the material removal takes place on the work surface, what is going to happen? So the work is now going to recede from the original surface, isn't it? So of course, कब ये होगा? When the material removal is going to start. Now this work surface is going away from this tool surface, that is receding of this work from this tool surface is definitely going to happen. And by how much velocity is going to recede from the tool surface? So that can be given with the say the material removal volume to the surface or to the area, which will give us this velocity, by how much, with which velocity is going to receding from the tool surface. So if I say that this receding velocity, it's a q dash, which is equal to material removal material removal volume, or material removal or volume which is get removed from the work divided by the area, so definitely you will get what? This is centimeter cube per second into area centimeter square. You will get this velocity with which it is going to receding from the tool surface, centimeter per second. And of course this gap between this work and tool, isn't it? So how this gap is going to change? The rate at which this distance between this work and tool is going to change. How we can get this? So we can have the rate at which the gap between these electrodes are changing is given by actually this dy by dt, that is gap y changing with respect to time when removal is starting, material removal is starting. So which is equal to aj divided by rho fz minus this field velocity f. Okay, so this is this dy by dt, that is change in rate of change in this gap, okay, that is distance y. So here j, we know what is value of j, that is a into k into v minus delta v divided by what is there, y is there, and this rho f z. So if I write like this, that is k a into bracket v minus delta v divided by rho f z, I will put it in this bracket into 1 upon y, this y minus this f. Okay, see here, if I put this term in the bracket as lambda, so what I can write? This dy by dt is equal to lambda by y minus f. So this equation is known as the equation of dynamics of electrochemical machining. Okay, so this is the equation known as the equation of dynamics of electrochemical machining. So here see, now we can have the variable cases. So if I take say case number 1, if I take the case number 1 as, say when this feed is 0, the feed for the workpiece or this feed velocity small f is 0. So what will happen if this feed is 0? So what we can write? This dy by dt is equal to lambda by y. Okay, so solve this equation. How to get the value for y? Then we have to integrate it, isn't it? So I will write here. So this integral y dy is equal to integral lambda times dt. And of course, if you look this time versus the distance, this is y and this is time. So this graph will look like this. So this is what? At t is equal to 0, this is the gap y naught, that is the initial positions of the electrodes, that is work and tool. So, and of course here t is the times, then y is the function of t. So what is the integral of this? That is y square upon 2 is equal to lambda times t plus c. Now put the boundary conditions. When see t is equal to 0, when t is equal to 0, this y becomes y naught, y becomes y naught. Therefore this y naught square by 2 is equal to 0 plus c, isn't it? So put this value in this equation, that is y square by 2 is equal to lambda t plus y naught square by 2. That is what I can get, y square is equal to y naught square plus 2 lambda, or y is equal to under root of y naught square plus 2 lambda. That is what the gap changes with. So gap between the tool and workface is changes with respect to time. Okay, now if I take the second case, that is so we are having the constant feed with the constant feed is there. Of course, in the practical situation, the feed should be uniform or constant. Otherwise, the non-uniform or variable feed is not actually desirable in case of the electrochemical machining. Say when I am saying the constant feed, so what was the equation of dynamics? That is dy by dt is equal to lambda by y minus f. So here if the constant feed is there, so जितना भी गैप चेंज होगा उतना ही क्या रहेगा वहां पे मटेरियल रिमूवल रेट रहेगा. दैट इज हाउ मच दिस distance between the two electrodes, that much we are having the material removal onto the work surface, isn't it? So that is, this gap is always going to be same, that gap always to be same between the tool and workpiece. Therefore there is no change in the gap between this workpiece and tool material or tool. Therefore this is to be 0. Okay, so if this is 0, then I can write, and of course when this gap is going to be 0, so whatever the distance between these two electrodes, that is the distance between the workpiece and the tool, is going to be what now? It not only y, but it is now in equilibrium. So this y will be get replaced by the ye, that is there is an equilibrium distance between the electrode and the, that is two electrodes, which is keeping this distance between them is always constant. So जितना मटेरियल रिमूव हो रहा है उतना क्या हो रहा है, तुरंत adjust हो रहा है वहां पे gap, isn't it? So here if I write this lambda by y, because it is 0, so lambda by y is equal to f. So what is this f? See this feed, and y is now going to be replaced by ye, because constant gap always, so they are two are in equilibrium, so y is becomes ye. This is the equilibrium gap. So this f is equal to what? This, or I can write this ye. If I want to find out the equilibrium gap between this tool and the workpiece, then it will be what? Lambda divided by f. And what is my lambda? Lambda is this k a v minus delta v divided by rho f z into this 1 upon f into 1 upon f. I will write here. So this is the equilibrium gap. Please remember, very important, this equilibrium gap, how to calculate equilibrium gap. So this is a formula where K is the conductivity, A is the gram atomic weight, V is the applied voltage, delta V is the over voltage, rho is the density of anode, that is workpiece material, F is the Faraday's constant, Z we know valency of the ions displaced, and F is what? The feed velocity or feed rate directly you can say, that is centimeter per second. So these are the two important cases, but generally see, if we look at the surface of the tool surface and the work surface, they are not always flat, so there are always some irregularity is there. Okay, and when these two electrodes are nearer to each other, definitely at some points there is a contact between these two. Okay, so see, in practical situations, so what was in our diagram? It was a tool, so it was a workpiece, and here it was a tool. Okay, so in practical situation, see, so this face or the surface finish, or ideally they will not be the flat, isn't it? Because some surface irregularities will be definitely there. So when these irregularities are there, and when these two electrodes or work or tool are coming closer to each other, so sometimes they get touched at these irregularities and the sparking will occur. Okay, so for that reason we have to keep the nominal gap between them, which is nothing but our what? Equilibrium gap. Can be shown like this. Say it is the surface of the workpiece, and this is the, see here, this is the surface of, say this is the work and this is the tool, and the surface irregularity, say this is in microns, say this distance I am having, say A in microns, micrometer, and this distance say it is having B for the tool. These are the irregularities present on the tool surface. It is in micron. So this distance, actually this distance is the nominal gap, and this distance actually we take it as, when solving the questions, this is the equilibrium gap, that equal to this A plus B. Okay, so this is in micron actually, so I have to get it into centimeter. So please remember, so here all the electrochemical machining, whatever the formulas I have given in CGS. So the length in centimeter, weight in gram, and time in second. So try to have in all the lengths, velocities in centimeter per second, isn't it, and weight in grams. Okay, and whatever, if they are asking to convert into, say they are asking in millimeter, they are asking in minute, so we can able to convert later. Okay, so this is actually the gap, nominal gap is nothing but the equilibrium gap between the electrode surface है, electrode कौन से है, tool and workpiece. So ये है nominal distance. So simply nominal gap we have to add these distances. Okay, A plus B, and put here to find out if this is known, then what they can ask the feed rate in centimeter per second or meter per second or millimeter per second, in any unit you can able to change. So this is about the kinematics and the dynamics of electrochemical machining. Very important, many times they are asking the questions on this formula. Okay, thank you.